Okay, so complex waves today, we're going to focus on circuits like this here that have resistors in, capacitors and inductors, right? So we have a value for R, a value for C, a value for L, and we know from what we understand about these sorts of circuits that as charge flows around the circuit, it goes off and on the plate on the capacitor, and as the charge flows off and on the plate on the capacitor, as the changing currents going through, there's some induced EMF. And so there's two real effects on this circuit. As the current changes around the circuit and the charge is sloshing about around this circuit, this capacitive and inductive effect comes into play. There's two formulae that we have that tells us what the reactance of the inductor is and what the reactance of the capacitor is. In other words, they're resistive effects. Can you remember what they are? Yeah, 2 pi FL, so where L is the inductance and 1 over 2 pi FC, where C is the capacitance. What's F? Frequency. So the frequency of the supply determines the reactance of these things. So if I change the frequency, I change the effect of this capacitor and inductor in the circuit. And that's what we're going to focus on today, really on that change, how that frequency affects it and what the consequences of that is. So the first thing I want you to do is to actually, if I give you some values, work out what's going on in this circuit. So, given some values, if R equals 2 ohms, L equals 500 millihenries and C equals 2.25 microfarads, I just want you to calculate the current in that circuit using complex numbers. If I tell you that the supply voltage is given by a wave function, and that wave function is 230 sine 100 pi t. So I'll just pause for a minute and let you think about it, and then we'll have a look at it together and work out what that current is flowing in the circuit. It's to do with complex numbers, and we also have to think about, you know, these values. What are these values in here telling us effectively, so we can work out what it is. So to start with this then, remember what this is. This is omega, the angular velocity. And what's the relation to the angular velocity and frequency? Omega equals 2 pi f. So we can find the frequency, which we need to be able to calculate the reactance in the circuits, and then we can calculate the current. So I'll pause again and let you see if you can carry on from there. You have to try and express the resistance in terms of complex numbers. Think about what the reactance XL and XC are, the complex numbers. Remember that the total impedance of the circuit, Z, when you calculated XL and XC, the total impedance is R. Remember, the resistance is the real part of the complex number, and if we work out what XL minus XC is, then that's the imaginary part of the impedance, okay, with the J value, in other words. So carrying on, calculate Z, and then once you've got Z, you can work out the current using Ohm's law effectively. So if we do this, we work out that XL turns out to be 50 pi, XC turns out to be 1414.7, both in ohms because they're reactances. So I subtract XC from XL and I get minus 1257.6 J. So in other words, the overriding influence in the circuit seems to be a capacitive effect. That's the big of the effects. So that's the impedance. Now I want to use Ohm's law to work out what the current is. So it's probably a good idea to convert this impedance into polar form, so we can do it more easily. The voltage will be 230 volts, so we can calculate the current. Again, I'll just pause while you finish that off. So, converting the impedance to polar form, we get this. Now let's just pause and think about this for a minute. If we think about this on some axes, what I'm saying is, remember, this is the real axis, and this is the imaginary axis. And so what I'm doing is I'm saying I've got an impedance of 2 along the real axis, so I'm going along 2 along the real axis, and then minus down 1257 on the imaginary axis, so way down here somewhere. So in fact, the line would be right down like that. So it's not surprising that the length of this line is around about 1257, and the angle is almost minus 90. So I was expecting something like that, to round it to the nearest degree, that is minus 90 degrees. So I expect that from this axis. Remember when we put the voltage in, the angle associated with the voltage is 0 because we're finding out what the phase angle is, or what the phase difference is between the current and the voltage. So the voltage is our reference, taken as 0. So what we're effectively saying is that there is a current of 0.18 amps, and it's leading the voltage by almost exactly out of phase, 90 degrees out of phase. Okay? Okay, so that's the story so far. The size of this current depends on the frequency, because the frequency determines the values of XL and XC. Agreed? So if I change the frequency of this supply, I'm going to change the current. And so it might be useful to think about, well, what frequencies are going to give me the maximum current that's coming out of here, and what is the size of that current? So that's what the sort of thing we're going to be discussing. Before we do that, I'm going to just talk about waves in more general terms. So I'm going to pause this video here, and then I'm going to talk about waves on slinky springs. So if you're watching this video, you might well want to go to a Google site and just type in waves on slinky springs, and you'll see longitudinal and transverse waves. Just have a look at them. Okay. Here's a picture of a slinky spring. So these represent the bars on the slinky spring that you will have seen on the video, hopefully. And the distance between one squashed up region on the slinky spring and the next squashed up region, if you like, it's called a compression in the physical sense. And the next is equal, and that's called a wavelength, so lambda for the wavelength. So that's the wavelength of this thing. And the frequency comes from something called the wave equation. C is the speed of the signal or the pulse through the medium. So that depends on the physical properties of the medium. In an electric circuit, things like the resistance, the capacitance and the inductance. But in a mechanical system, the density, the temperature, the pressure, the physical conditions determine the speed of the wave, and the frequency equals the speed, which is a constant for a given set of conditions, divided by the wavelength. So small wavelengths the smaller the wavelength, the bigger the frequency. I increase the frequency of this signal, I decrease the wavelength, the distance between one pulse and the next. For a given set of conditions in a given circuit, for example, there is a frequency at which a pulse would like to travel up and down the wave. And that's called its natural frequency. So every physical situation, or every physical system, and that an electric circuit is no different to enter a physical system, that is a physical system. Every physical system has a natural frequency. Let's call that Fn, subscript n for natural frequency. we can drive a system at any frequency we like. So I was making the slinky spring pulse at any given frequency. Any physical system, we can drive it at any frequency we like. But interesting thing starts to happen when that driving frequency, so let's call the driving frequency FD for driving, things start to happen when the driving frequency equals the natural frequency. Then we get particularly large oscillations in the system, and in the circuit particularly that's associated with particularly large currents. So, and that's when we get what's called resonance. So resonance occurs when the driving frequency equals the natural frequency. So that's an interesting point, when we're driving a circuit at a natural frequency. So in a physical system, when resonance occurs and the natural frequency equals the driving frequency, we get large oscillations and large currents, as I've said. A physical system might be something like a bridge, and there's a very famous little video sequence about a bridge that collapsed when the wind that was flowing through or round the bridge actually got this thing to oscillate at its natural frequency. The physical properties of the bridge meant that its natural frequency, it was able to oscillate at its natural frequency, and that caused all sorts of nasty things to happen. You can see it there, isn't that incredible? It couldn't survive, obviously, and so in the end it collapsed. But if you think back to the slinky spring, you can actually see the oscillation similar to what we saw on the slinky spring. This is an example of a transverse wave. So it's not only oscillating along the length of the bridge, but also transverse across it. Yeah. The bridge was called Galloping Gertie because for months after it was built, when the wind was blowing, it used to do that. So it got a name, a bit like the Millennium Bridge that used to oscillate. Yeah. So it was given this name, Galloping Gertie, but eventually it got to the point where the wind conditions were just right. Yeah. Yeah. I'm not sure what that is. Oh, it's the cable going up. Yeah. 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 It's a hell of a name, isn't it? Make him out here, I think. Make him out. I won't spoil the end of the video, but if you look it up on Google, you can see what eventually happens to the bridge, and you can predict what's going to happen. it was, yes, because of this, the lengths of the span fitted perfectly with the natural frequency of the roadway. So when you started it to oscillate, it oscillated at its natural frequency. So now bridges are designed so that the lengths of the things don't match natural frequencies yet. Okay, so let's have a look at this and how this relates to electric circuit. Resonance occurs when the driving frequency equals the natural frequency. So you can imagine, having looked at that video, that it would be handy to know what the natural frequency was. So in some circuits we can either look for the natural frequency if we're trying to tune a circuit in, for example, to a particular frequency, radio tuning, or we can avoid driving the circuit at those frequencies because you're going to get these large currents. So if we look back at our circuit, we are driving this circuit at this particular frequency. So if I look again at this wave function here, this is our driving frequency in here. So what is the frequency at which I'm driving the circuit? 50 Hertz. What we need to do now is to find out what's the natural frequency of this circuit. So let's focus on this, because that's going to help us work out what the natural frequency of the circuit is. So Z, which is the total impedance of the circuit, is given by this function here. So let me just rewrite this function and we'll have a look at it. So there it is. This is the total resistive effect of the circuit, which is a combination of the real resistance and the reactance of the system due to the charges oscillating. So this effect comes into play, doesn't it, when we've got an AC circuit, not when we've got a DC circuit. So we're talking about charges oscillating backwards and forwards around this circuit. There's not a hell of a lot we can do about the resistance of the circuit. That's due to the physical properties, the pure resistance of the circuit. What we can affect, though, with the frequency, as we've talked about already, is the reactance of the capacitor and the inductor. If you think about when we want maximum current, what situation here would give us maximum current? What's the smallest value Z can have? If you remember, we've got this is the impedance of the circuit, which is made up of the pure resistance, which goes along here, and the reactance, whether it be total reactance of inductive or capacitive. So in our case, actually the triangle is going downwards, isn't it? But it could easily be going upwards. Whoops, that's not what I meant to do. It could easily be going that way. In fact, in our circuit it is, isn't it? So the overall impedance actually was way down here somewhere. The real part of the circuit was very small. All the effect was due to the reactance, which gave us a very large total impedance, didn't it? What's the ideal value for the reactance to give us the smallest possible value for Z, and what is the value of Z? The smallest value we can have for Z is when this angle is 0. And when does that occur? It occurs when XL equals XC, because then they cancel each other out, these two effects here, and we've just got the resistance that lays along here. So in other words, if we think back to our circuit, which was here, we had a resistance of 2 ohms. So the smallest value Z can have is 2 ohms when XL equals XC, in other words. So And that's the natural frequency. The natural frequency occurs when we get the largest possible current, and the largest current is when we've just got the resistance and the capacitive effect is matching the inductive effect effectively, and they're matching each other is when they're equal to each other. So we get the natural frequency occurring when XL equals XC. And we know a formula for XL and XC. So for this particular circuit, remember we have values for L and C. We can write in the formulae. So we've got 2 pi FL equals 1 over 2 pi FC. I'm after F. I want to get F on its own. So let's think about this equation. Now we're talking maths. What would I do to try and get F on its own? Ideas. I want to get F on one side. So what would you do? Multiply both sides by F. That would get rid of the F underneath on this side. What would I end up with? Write it down. That gives us this, because I've brought the F up to the left hand side, and so we've got F squared. So now I want to get F squared on its own, so first, before I do that, I've got a square root in the end, but what do I do first? By 2 pi L. Yeah. Get rid of the 2 pi L by dividing both sides by 2 pi L. So see what you're left with, and then square root. So see if you can carry on and finish that off, and simplify it as far as possible. I'll just pause while I have a go, and then I'll do it. So if I divide both sides by 2 pi L, I get this underneath. So as well as 2 pi C, I've got 2 pi L. Combine the 2 pi's together to get 2 pi squared CL. And then finally square root, so I get 1 over 2 pi root LC or CL, whichever way around, doesn't matter. We can actually go one little step further, actually, and that's it now. That is the natural frequency, and that's an important formula that we'll be using in a second. But actually, often, if I were to multiply both sides now by 2 pi, I'd end up with 2 pi natural frequency equals 1 over the square root of LC or CL, whichever way around. And remember what 2 pi F is, it's the angular velocity. So we've got another formula that's often quoted, that the angular velocity at which natural frequency occurs equals 1 over root LC. So for any circuit, I can find the angular velocity at which it would naturally oscillate at by just dividing 1 by the square root of L times C for any particular circuit. And if I wanted to know what the natural frequency was, I'd just divide that by 2 pi. In other words, I use this formula here. So what I wanted to do now is use this formula and the values in the circuit we had to find out what the natural frequency of this circuit is. And I'll just pause while you do that. So for our circuit, where we had R equals to 2 ohms, C equals 2.25 microfarads, and L is 500 millihenries, put those values into that formula we had. The natural frequency is 1 over 2 pi root LC. We get 150 hertz. So that's the natural frequency of this circuit. Well, that's a relief, because we're driving it at 50 hertz. However, it turns out that 50 hertz is a multiple of it goes into 150, so that might cause problems. And remember, when we were talking about the slinky spring, we had not only the fundamental frequency, the natural frequency, but harmonics on top of that. And so we're going to find that's going to cause a problem. Okay? And I now want to talk about this idea of the complex wave, which is what this is all about, really, because any wave system, a complex wave, is made up of its fundamental wave with a natural frequency and harmonics on top of it. So there's a handout I'm going to give you now on complex waves to introduce them, and that's this one here. I'll just pause and hand it out. So I'll just pause this video and give you a chance to just literally read this. So having read it, we can see that any system, we're talking about waves and oscillations, we can analyze these waves using Fourier transforms. And we'll be going to do some of that next week. We're going to look at Fourier transforms and how we can apply a Fourier transform and analyze a complex wave. We'll be looking at a square wave and a sawtooth wave, which are common waves that we put in. How can we take a square wave and a sawtooth wave and break it down into its individual waves? So focusing on this particular picture at the start of the handout, i.e. this one, that's sort of what's happening here. If we look at this complex wave here, if we think about that, that's made up of a wave, another wave, and another wave. And if we think back to our slinky springs, look at this distance between here and here. The physical properties of the wave depend on the medium it travels through, but also, in this particular case, the length. So the length is the same for each of these, over which the wave is acting. But what I have here is, well, not the fundamental actually, because the fundamental looks like this, as we saw on the slinky string. That was the fundamental. The first harmonic actually looks like this, which is this one. And this would be the second harmonic and the third harmonic, and so on. And the combination of the fundamental and its harmonics make up the complex wave. And you can sort of see how that's happening here. We've got the overall wave behaves a little bit like this one, but then on top of that are these other ones. So it's a combination of the two. And if we get just right, we can actually end up with a square wave pulse, which is maybe what we want, and we'll be looking at that next week. So what we have is a situation where the wavelength is some multiple. We want wavelengths so that they fit directly into these dimensions, and so the frequencies tend to be doubling up. So if you have a natural frequency of 50 hertz, say, then the first harmonic might be the wavelength. If we look at the wavelengths here, the wavelength is halved. If we think back to the fundamental looked like this. So effectively half the wave is fitted into this distance. Here, a whole wave is fitted into that distance. So if the wavelength is halved, thinking to that equation for the speed, frequency, and wavelength, the frequency would double. So the frequency is 100 hertz. The next one, 1.5 waves fit on, so the frequency will be 150 hertz, and so on. So the harmonics tend to be multiples of the natural frequency. And we found in our circuit, yeah, exactly, we found in our circuit, didn't we, that was the natural frequency. So we're going to have problems with our circuit, even though we're driving it at 50 hertz, because of possible harmonics. So the last thing I want us to do today is to work out what current will flow in that circuit if we had a frequency of not 50 hertz but 150 hertz. So go back to the calculation you looked at the beginning of today and repeat the calculation with a frequency of 150 hertz and see what happens. And I'll pause while you have a go at it. So if we look at the circuit, if the frequency is now 150 hertz, and we find out what XL is, so using a frequency of 150 hertz, XL turns out to be that, 471.2 ohms, And XC turns out to be 471.6. Note, about the same. And do you remember we were saying for natural frequency for resonance, we wanted XL to be roughly equal to XC, and that's turned out to be the case. So they're virtually cancelling each other out. So the total impedance is going to be near enough to, because that's the resistance of the circuit. And so that's 2.03. There's a slight reactive effect, and there's a slight phase angle, 10 degrees. So what's the current? It's 230 divided by 2, which gives us 113.3 amps. Yeah, that's right. And you probably wouldn't want that sort of current flowing around the circuit because you're likely to damage it. So if there are any harmonics around of about the third harmonic in this circuit, you're going to hit problems and you might damage the components. Yeah, that's right. We're driving. Yes, exactly. We're driving at not the natural frequency but the third harmonic, which is a multiple of the natural frequency, because the natural frequency is 50, remember? And so, sorry, the natural frequency is 150 rather, yeah, and so we were driving it at 50, and it's likely that within there would be the harmonic, so we're hitting the natural frequency of the circuit. Yeah. Worse than that, let's just calculate what the voltages are across. Remember, we've got 230 volts. Here, that's our supply voltage. We've worked out that the current is 113 amps, near enough. So what is the voltage across the capacitor and the voltage across the inductor? How would you work that out? Yeah, I times the reactance of the capacitor, I times the reactance of the inductance. What's the voltage across each of those components? V equals IR. Yeah. So E, we're talking about E, equals I times the reactance. Yep. And the same for the capacitive reactance. What does the voltage turn out to be? Let's pause while you work it out. If we calculate it, we get 53-ish kilovolts across the inductor and the capacitor. And our supply voltage, remember, is 230 volts, so yeah, 230 volts across there is nearly all across there, but we get these huge voltages. So our supply volt, think back to the, we were talking about sloshing circuits and sloshing water in a bath. You know, you didn't need, once it's going, you don't need to put much energy in to keep the system moving. And in fact, the energies build up until you get these massive voltages across the components, far greater than the actual supply voltage we're putting in. So we're going to damage circuits if we allow this thing to go unchecked. Okay, so we need to take precautions. Okay, so today was all about this idea of finding the natural frequency of a circuit, and it's important to find the natural frequency because we might end up, particularly when we're putting complex waves in a circuit, by hitting these harmonics, and so we've got to take them into account. And more on this next week.